In this video, we're going to go over two examples of determining if a estimator is biased or unbiased. So from our previous lectures, we discussed an unbiased estimator, which was if we have some estimator, say we denote it with some parameter we're trying to estimate, which is theta, we give it a little hat to denote that that's our estimator. If we take the expectation of it, we hope that it would be equal to the true parameter of the underlying distribution. If that's the case, then we say that it's unbiased, and it's biased if it doesn't equal it. So let's do two examples. The first one that we have is we have a random sample x1, x2, all the way up to xn. They're random variables that are independent and identically distributed with mean mu and variance sigma squared. We need to show that the estimator, s squared, is equal to 1 over n minus 1 summation of from I equals 1 to n of xi minus x bar, or that's the sample mean, all squared. We've seen this before. This is the sample variance. As opposed to the population variance, where we have a factor in front here with 1 over n. We're going to show why we have this 1 over n minus 1. So we want to show that it's an unbiased estimator. So what we're going to do is rewrite s squared. So we start out with this, and we're going to make sure that I have the squared term on there. We can rewrite this. There is a formula in our textbook that we can use, which is, they refer to it as the shortcut formula. But we can also express this as 1 over n minus 1. And again, we're going to just break up this summation. And then I have the summation so squared all over n. Now, what we need to do is we're going to take the expectation on both sides. So doing that, if I take the expectation, here's the expectation of our s squared. And again, we just take our expectation and the hope is that we'll find out that this should be equal to our parameter that we're trying to estimate, which in this case is sigma squared. So we just need to remember our rules for expectation, so we can start to apply it. We basically have a constant here because what we're interested in is the random variable x is what we are applying this operator to. So in this case, this is treated like a constant. So we can bring that out front. And then I'm left with everything on the inside there. Okay, so we can keep going with that. So now I'm going to apply the expected or expectation operator to each of these terms on the inside. So inside here, what I end up getting is the summation. So I have xi squared. So again, there's the expectation of xi squared minus, now I have 1 over n here, so I can bring that out in front. And then I'm left with the expected value of the summation of the xi all squared. Okay. Now, we need to recall some formulas about variance. So again, we have to recall. So we had the shortcut for variance, which was if I have v of x, that's equal to the expected value of x squared minus the expected value of x squared. And we can rearrange that. So I could just bring this over to the, I'm just going to leave it like that. And what that means is over here, the variance is what we were given, which is the variance is sigma squared. And we have the expectation of x, so that's mu squared. So we have that. So I can substitute that into in through here. So doing that, so what I get is that the expectation of s squared is equal to 1 over n minus 1. And now on the inside here, okay, so I have the expectation of xi squared. So I can expand that out. So that term becomes sigma squared plus mu squared. Then we have this term over here. We have the minus 1 over n. And again, we have the expectation of xi. And let's just correct that. Okay, well, we have the summation. It doesn't really matter, so we can leave it like that. And then on that inside there, I can expand this out because it's the summation of xi all squared. So same formula here I can apply. So in this case, what ends up happening is we have v of x, but it's a summation of the random variables. So we have the variance of the sum of those variables. And we add the expectation of x, and again, this is just a summation of our random variables. And then we square this. So we're almost finished. It may look a little bit ugly at the moment, but what happens is, well, we're going to sum over. We have sigma squared, so that's a constant. That happens n times, so that will be n times sigma squared plus the next one we have here is mu squared. That's still a constant in this case. That happens n times, so n mu squared. Then we have our minus 1 over n. And in this case, we already know what the variance when we have the sum of random variables here. Again, that happens. The variance is for each of these terms is sigma squared. And since these are independent, we can add them up. So the variance of each individual one is sigma squared, and that happens n times. Plus, now we have the expectation of the xi, and it happens n times, so we're going to have n times mu squared. So what we can do then is let's just expand that out. So I get n sigma squared plus n mu squared minus, okay, so now when I distribute the 1 over n onto each of these terms, what I get is the n's cancel, so I'm left with sigma squared. And over here, I'll get n squared mu squared, but that one end cancels, so I'm left with n mu squared, which means that, oh, and I still have the n minus 1. What happens then is that this n mu squared minus n minus mu squared cancel, and I'm left with n sigma squared minus sigma squared. So let's factor that out. What I'm left with is n minus 1 all over n minus 1. That cancels. And so we get that the expectation of s squared is equal to sigma squared. So what we've shown is that s squared is an unbiased estimator of the variance. Okay, so let's do another one. Very similar again. So while we were looking at the sample variance, where the sample variance has 1 over n minus 1, we're now going to look at the case where we have, essentially this is the variance, but in this case it's 1 over n. So not only are we asked to show that it's biased, but we're also asked to calculate what amount of bias it has in it. So to do that, so we start out with this as a solution. So for that, what we need to show that the expectation of this estimator is not equal to sigma squared. So the way that we're going to do that is we're going to express this in terms of s squared. So now to do that, okay, we start off with 1 over n. So we write it out. And I need to manipulate this a bit so that I can get what I want. So I'm going to use 1 over n. And I have 1 over n. So what I would like to do is to express it in terms of s squared. I need to get some term of 1 over n minus 1. So let's do that. I'll write 1 over n minus 1. But to do that, I can't just, to make this equal to one another, I can't just do that. So I have to have the n minus 1 here. So again, that n minus 1 and that n minus 1 would cancel, and then I'm left with 1 over n multiplied by that summation. So that gives me the original estimator that I have. Then that means over here, that's s squared. So I can express that as n minus 1 over n multiplied by s squared. Now, let's take the expectation of this. So now we have n minus 1 over n s squared. Now we can apply this linear operator to it, the expectation of it. So we have that this is a constant. So we have n minus 1 over n multiplied by the expectation of s squared. Again, just remembering that if I have some constant times a random variable, then that's a times the expectation. So that's what I've done. But from our previous example, we already know that the expectation of s squared is sigma squared. So let's write that in. We have that is equal to sigma squared, leaving my n minus 1 over n. But unfortunately, we have that term n minus 1 over n because we have this term here that's definitely not equal to sigma squared. So we can conclude, since the expectation of our estimator is not sigma squared, well, then that means that this estimator is biased. So we're not quite finished yet because we have part B, which is calculate the estimator's bias. So to do this, it's the difference between our expectations. So the bias is the difference of our expectation of our estimator minus our true parameter. So in this case, so here's our estimator, and over here, that's our true parameter. And we've already calculated this, which we showed was n minus 1 over n sigma squared minus sigma squared. We can factor out this because we have a sigma squared and sigma squared, so I'm left with n minus 1 over n minus 1. And so I can have this as n over n. So I'll have n minus 1 minus n. This cancels. So what that equals is minus sigma squared over n. And that's our bias. So those are two examples showing estimators where it's unbiased and biased. So again, for those that we had deferred talking about the sample variance, why it's 1 over n minus 1, it's because it helps to make sure that it's an unbiased estimator. And by the general principle of estimators, we prefer to have unbiased estimators. So in this case, that sample variance leads us to have an unbiased estimator, whereas if we just have 1 over n, then it's a bias. So that concludes our two examples. We'll continue with our next video.